So Froza, did you try that assignment that I gave yesterday? So did you try that assignment that I gave yesterday? Froza, Jubana? Good afternoon. Jubana, did you try that assignment? No. Afroza, did you try that? I'm asking because should I take doubts today or the next week?
Next class.
Next class. Afroza? So, okay. So that theoretical part is over. The theoretical part have drift velocity, the definition of resistance and that temperature dependence. The next topic is EMF of cell. So EMF, the full form of EMF is electromotive force. The full form of EMF is electromotive force. This term is somewhat misleading. EMF is actually not a force. EMF is a potential difference. This term is misleading. EMF is basically the maximum potential difference. Basically, the maximum potential difference across the terminals of cell. Across the terminals of cell. So the maximum potential difference across the terminals of the cell is known as EMF, or this is electromotive force. So if I take a cell and I call the EMF of the cell is E, then the EMF means this longer terminal is at higher potential. The shorter one is at lower potential. The potential difference between this higher and lower terminal is known as EMF of the cell. This is the definition of EMF, with the maximum potential difference across the terminals of the cell in open circuit. Cell in open circuit. If I take an example, say I'm taking a cell and I'm writing the EMF of the cell is 10 volt. So this volt simply means 10 volt means this is higher terminal, this is lower terminal. So the potential difference between higher and lower terminal is 10. This is it. So it's the potential difference between higher terminal and the lower terminal is 10. This is what we mean by EMF of the cell. But the important thing is to define EMF. Your cell should be in open circuit. Means you're not withdrawing any current from the cell. Because once you start withdrawing current from the cell, then potential difference may change. But if you are not withdrawing any current from the cell, then potential difference will not change. So EMF is maximum potential difference across the terminals of the cell in open circuit. VH minus VL is 10 volt. Is it clear? Both of you?
So the same thing goes with capacitors and resistance.
Yes, potential difference is same, but in capacitor, that potential difference is not EMF. We call that potential difference as voltage. In resistor, the potential difference is not EMF. That potential difference is voltage across the resistor. But in case of cell, that potential difference is the EMF of cell.
Okay, sir.
So, and there's one more important thing. While writing potential difference of the capacitor, it's no need that the capacitor should be in open circuit. No need to define this condition that you are not withdrawing any current from the capacitor. For resistor, there is no condition like resistor should be in open circuit. But for cell, To define EMF, this is an essential condition that your cell should be in open circuit. Why this cell should be in open circuit, this we will consider in the next section when we study terminal potential. So is it clear? EMF.
Yes, sir.
After EMF, the next is internal resistance. The next is internal resistance of cell. So internal resistance simply means if I take a cell, do you know, have you done electrochemistry in your class? Chemistry, electrochemistry. Have you studied electrochemistry? Yes, no, no. Okay. So in electrochemistry, you will study how we make a cell. Basically, a cell consists of an electrolytic solution. If I take a cell, then to make cell, we take an electrolytic solution, a solution which is known as electrolytic solution. Electrolytic solution. And we consider two electrodes. Electrolytic solution and two electrodes. This is how we make a cell. I have not connected this cell with an external circuit, but these, okay, you have studied in previous class. So we have not connected this cell with an external resistor, but this electrolytic solution and these electrodes will itself provide some resistance, which is known as internal resistance of cell. These electrodes and these electrolytic solution will make a resistance, will offer a resistance which is known as internal resistance. Say I'm not connecting this cell to an external supply. The cell only. Electrodes and electrolytic solution are the parts of cell. The resistance offered by these electrodes and electrolytic solution is known as internal resistance of cell. So internal resistance is the resistance offered by electrodes and electrolytic solution. Electrodes and electrolytic solution is internal resistance. With time or with use, internal resistance of cell increases. With use, internal resistance of cell increases. It happens now after some time you can't withdraw sufficient amount of current from your cell, or you can say that your cell is dead. So dead cell simply means the internal resistance is very high. As you keep on using your cell, its internal resistance keep on increasing. And once it's very large, the cell is dead. Means you cannot withdraw decent amount of current from your cell. I will say it's dead. So with use, this internal resistance increases. Okay, just note it down. And let me know when you have written. Sure. So can I raise it? So internal resistance of cell depends on internal resistance of cell depends on. So the first factor on which the internal resistance of cell depends is nature of electrolyte. It depends on nature of electrolyte. Then it's proportional to the concentration of electrolyte. It is directly proportional. It is directly proportional to the concentration of electrolyte. To the concentration of electrolyte. It is directly proportional to the distance between the electrodes. It is directly proportional to the distance between the electrodes. To the distance between the two electrodes. It is inversely proportional to the area of electrodes. It is inversely proportional to the common area of electrodes emerged. Fifth one. It increases with decrease in temperature. It increases with decrease in temperature of electrolyte. So these are few factors on which the internal resistance of your cell depends. It depends on these five factors: nature of electrolyte, concentration of electrolyte, distance between the electrodes, and the common area of electrodes. It increases with increase in temperature of electrolyte. Tell me when you have written. Can I raise it? Sure. The next is terminal potential difference. The next thing is terminal potential difference. Terminal potential difference. See what this terminal potential difference physically means. So physically, terminal potential difference means I'm taking a real life example. Say I take a cell of some 5 volt. This is the internal resistance. Okay, just do one thing. In the last section of internal resistance, just draw this diagram with cell. We connect the resistance small r and we call this small r as internal resistance. This is the internal resistance. With cell, I connected a resistance small r. I call this small r as the internal resistance. This small r is the internal resistance of the cell. So it's using this real life example. You take a cell of 5 volt. Through this cell, and this is internal resistance of the cell. I connected a bulb. So if the EMF of the cell is 5 volt, then ideally the voltage that is available for this bulb should be 5 volt. Ideally. Means if you buy a cell of 5 volt from the market, so we'll assume you will expect that this cell will provide a voltage of 5 volt to the cell or to the bulb or motor, whatever the device you are using. This cell will provide a voltage of 5 volt to that device. But with this cell, I connected an internal resistance small r. The cell has some internal resistance. So this is ideally what we are expecting. But really, this cell of 5 volt will not offer voltage of 5 volt to this bulb. The reason is, out of this 5 volt, some of the voltage will get dropped across this internal resistance of cell. Let's say out of 5 volt, 2 volt is dropped across the internal resistance. The remaining 3 volt will be available for the bulb. This available potential difference or this available voltage is known as terminal potential difference. This is what terminal potential difference mean in real life. If you buy a cell of 2 volt from the market, so those 2 volt are not, you cannot use that 2 volt in an external circuit. Like using that cell of 2 volt, you cannot run a motor which requires 2 volt. Because out of those 2 volt, a part of the voltage is dropped across the internal resistance. The remaining will be across the bulb or across the external source. So if I take a cell of 10 volt, this is the internal resistance of the cell. The voltage across the internal resistance is say 1 volt. So the remaining voltage 10 minus 1, 9 volt is available for the external device. This available potential difference, this available voltage is known as terminal potential difference. Did you got this point? Terminal potential difference. What does terminal potential difference physically mean? Afroza? Yes. So Afroza, if I take, see this example. If I take a cell of 10 volt, every cell will have some internal resistance. This small r is the internal resistance of the cell. So out of this 10 volt, some voltage will drop across this internal resistance. For example, let's say that 1 volt drop across this internal resistance. Then how much voltage is available? Out of 10, 1 drop across the internal resistance. So for the external circuit, you just have 9 volt, 10 minus 1. This 9 volt is the voltage of the cell that you can use. Because 1 volt is wasted across the internal resistance. So that voltage that you can use is terminal potential. So we define this as potential difference across the terminals of cell in closed circuit. So potential difference across the terminals of the cell in closed circuit is known as terminal potential. Or in a very language of layman, you can write this as this is potential difference, available potential difference of the cell. This is available potential difference of cell. For external circuit. You can write this as usable voltage. This available potential difference for external circuit is known as terminal potential difference. Now, how to calculate this terminal potential difference? Let's say I take this cell, the EMF of the cell is E, the internal resistance is small r, and this is your external circuit, right? This is external resistance, capital R. This is internal resistance of the cell. This is A and B are the terminals of the cell. So potential difference across A and B would be terminal potential difference. So VA minus VB, we will represent by V is terminal potential difference. Okay, Froza, if EMF of the cell is E, and I'm saying that voltage across this internal resistance is small, is IR. So can you guess how much is the terminal potential difference? EMF of the cell is E, voltage across the internal resistance is IR. So can you guess how much is the terminal potential difference? Or Froza? You can use the same analogy that we have used here. Instead of 10 volt, I'm writing E. Instead of 1 volt, I'm saying it's IR. So can you calculate the terminal potential difference? Froza? No. Giovanna, will you try?
E minus IR.
Right, E minus IR. The available potential difference, a simple thing. Total EMF minus the voltage across the internal resistance, whatever is left is potential difference across the external resistance. So if I is the current through cell, if I is the current through cell, then you can write this I as its E by its capital R plus small r. This is current through the cell, which is E by capital R plus small r. Okay, you also said I minus IR. I couldn't listen you. So I is, this is the current, E by, or let's not use this value of current. So we can simply write that potential difference, terminal potential difference is total EMF minus IR. Means IR is the voltage across the internal. So this V is terminal potential. There's one more method to calculate terminal potential difference. You can even define terminal potential difference in this way. Terminal potential difference can also be defined as potential difference across external resistance R. You can even define your potential difference as the potential difference across the external resistance capital R. This is also terminal potential difference. That you can write as IR, and you can write your current as this is EMF, this is the internal resistance, this is external resistance. The total resistance of the circuit is R plus R, so you can write your current as the current you can write is EMF by total resistance, it's E by R plus R. So you can write your voltage as it's E by it's R plus R into capital R. This is the expression of voltage. It's E by R plus R into capital. This is the expression of, these two are the formula for terminal potential. So clear? Both the relations and both the definitions. Yes, Giovanna, both the definitions are clear? Okay. Just note it down. We'll do some conceptual questions on this topic. Can I raise it? Okay, you didn't get the last equation. See, Jumana, I want to calculate the voltage across this external resistance capital R. To calculate voltage across this capital R, first of all, we need to calculate current I, which is EMF divided by R plus R. I need I, which is E by capital R plus small r. Current is EMF divided by total resistance, right? The total resistance of the circuit is R plus small r. That's why current is E by R plus R. Then the expression of voltage is current into resistance. So instead of current, I just substituted E by R plus R and I multiplied with capital R. This is the expression of voltage. So is it clear, everyone? Next, we have some special cases here. Case 1. In open circuit, means you have to calculate terminal potential difference if your cell is in open circuit. Open circuit means this is internal resistance, this is external resistance. I connected a key here and this key is open. And this key is open. This is R, this is small r. Okay, how much is current in open circuit? Answers, how much is current in this open circuit if your circuit is open? What's the value of current? How much is current in open circuit? Open circuit means you off the switch. Your current would be 0. So V is E minus IR. If I put I equal to 0, then V would be equal to E only. So this is the potential difference in open circuit. In open circuit, your V is equal to E only. The terminal potential difference would be equal to EMF of the cell. That's an open circuit. Case 2. If I take short circuit, short circuit simply means, if I say this term short circuit means I replace resistor with a straight wire. If I take short circuit means replace resistor with a conducting wire. So will you tell me what's the resistance of a conducting wire? Ideal conductor, perfect conductor. So what is the resistance of a conducting wire? If I replace your resistor with a conducting wire, what the resistance of the resistor is R. What's the resistance of the conducting wire? Afroza, Jubena. What is the resistance of the conducting wire? Well, its resistance is 0. Jubena, if you have a conducting wire, an ideal conducting wire, when we use a wire in the circuit, that means we are using an ideal wire. An ideal wire have 0 resistance. Is it clear? And this is an ideal model because no wire is ideal. But while using wires in circuit, we take this approximation that your given wire is ideal. If your given wire is ideal, that means it has 0 resistance. Is it clear, everyone?
Yes, sir.
Okay, so I put R equal to 0. So if I put R equal to 0 in this particular equation, then your current comes out to be, this is small r, internal resistance. The current would be E by small r only. And you would say that your current is maximum in this case. This is the maximum current because your resistance is minimum. Earlier it was small r plus capital R. Now this capital R is 0. There's a minimum resistance. Your current will become maximum. If I use this value of current in this expression, V is equal to E minus IR. Try using this thing instead of I, just substitute E by R and tell me what is V. Try solving this. Instead of I, put E by R and try to calculate V. Very good. Jabana, your answer? Very good. So this is E minus E by R into R. So gets cancelled out, your V comes out to be 0. So in short circuit, terminal potential difference is 0. There's one more thing, case 3. The case 3 says, so this is open circuit, this one is short circuit, and the case 3 says during charging, discharging. Usually a cell discharge, like the current in the cell flows in the circuit. So the electrical energy of the cell keep on decreasing with time. This is known as discharging. Discharging means electrical energy of cell, electrical energy stored in cell goes to circuit. Discharge. This is the meaning of discharge. If a cell is discharging, then remember that the direction of current during discharging is from positive to negative terminal. When I say positive to negative terminal, that means through the circuit, not through the cell. You can't go from positive to negative in this way. That's the wrong method to analyze direction. To analyze direction, always move through the circuit. You're moving from positive to negative terminal through the circuit. That is the discharge. This is how a cell discharge. So discharging, if a cell discharge, then electrical energy stored in cell goes to circuit. And the terminal potential difference is E minus IR. This is what we have derived. We have derived for a cell which discharge. What if I charge the cell? Charging. So, okay, tell me, can a resistor charge a cell, or to charge a cell you need another cell? How usually you charge a cell? You charge a cell through a resistor, or you charge a cell through another power supply? Yes, both of you. Yes, we charge a cell through other power supply. Yes, we connect another cell. When we connect another cell, then during charging, the direction of current gets reversed. Say during discharging, the direction of current is this, positive to negative. This is the direction of current. But during charging, the direction of current gets reversed. Because now the current is due to another cell which is charging this particular cell. Your terminal potential difference instead of E minus IR becomes E plus IR. I cannot derive this result right now. We will derive this result once we start Kirchhoff law, Kirchhoff voltage law. When we start Kirchhoff voltage law, then we will derive this result. So I'm not deriving it right now. E plus IR. Just note it down. We'll do the next topic. Completed. Good. So, Afroza, can I raise it? Done? Okay. Let's do few questions on this concept of terminal potential difference. So always remember these four cases. If your cell is in open circuit, then terminal potential difference is equal to EMF. If your cell is short means you connected the two terminals of the cell through a wire. If your cell is short, then the current is maximum, it's E by R, but terminal potential difference reduced to zero. Third one, if your cell is discharging, then terminal potential difference is E minus IR. We have derived result for discharging. But if your cell charged, the terminal potential difference is greater than I. It will be E plus IR. That's the value of terminal potential. So the next question is, okay, solve this one. A battery of EMF E and internal resistance small r gives a current of 0.5 ampere with an external resistor of 12 ohm and a current of 0.25 ampere with an external resistor is 25 ohm. Calculate part 1. Internal resistance of cell. Part 2. EMF of cell. So I'm giving some hint for this numerical. So you take a resistor, you connected this resistor to a cell and with some certain internal resistance. So EMF is E, internal resistance is R, first external resistance is R1. So the first one is 12 ohm and you got a current of 0.25 ampere. You can write the value of the formula for current is E by R1 plus R. Then using same cell and the same internal resistance, he connected another external resistance of 25 ohm and now the current is 0.25 ampere. So you will have two equations and two variables. Two equations and two variables, one E and another small r. Solve them and get the value of E as well as R. Solve and report your answer in chat room. Answers, Froza, Joanna. No, Jumena, using two equations, you can calculate the numerical value of E and R. Right now, you're calculating E in terms of R. See, I is E by R1 plus R, right? So the first of all, your current is 0.5. So I can write your as E. EMF is E by 12 plus small r. That's my first equation. Next, we can write this as 0.25 is equal to E over 25 plus R. So you have these two equations. If you divide these two equations, you can get the value of small r. Just try to get small r now. I don't want to do these calculations. I want you to solve this. Just divide these equations 1 and 2 and try to get the value of small r. Are these two equations clear to both of you?
Yes, sir.
Okay, so now divide these equations, try to get the value smaller. Okay, Froza got 1.2. No, Froza, just check your calculations again. Froza, always double check your calculation. You, Jovena, what is smaller?
So I'm about to find it. Last step.
Okay. Froza, check your calculations once more. Answers, that lengthy calculation. What a lengthy calculation. 0.5 by 0.25, it's E by 25 plus. Okay, you just solve it and Jumena, this resistance cannot be negative. See, if I divide it, this E will cancel this E. If I remove this decimal, let's multiply it with 10 here. If I remove this decimal, multiply it with 100 here. So this is 100. It's 5 into 100 by 25 into 10 is 25 plus R by 12 plus R. So this 252 times 500. So you have 2 is equal to 25 plus R divided by 12 plus R. So if I multiply it here, it's 2 into 12 plus R is 25 plus R. So that's 24 plus 2R is 25 plus R. So your R comes out to be 1 ohm. This R comes out to be 1 ohm. Clear? Both of you?
Yes, sir.
What mistake you were making, Joanna?
I didn't convert decimal into numbers.
Even if you don't consider decimal into numbers, then it's 0.5 by 0.25. It would be 1 by 0.5. That's it. It should be 1 by 0.5. That you can write as 2. Anyways, now substitute this value of R in either of the equation 1 and 2 and get E. Just substitute the value of R in equation number 1 or in equation number 2 and get the value of EMF. I need EMF of the cell. EMF comes out to be 7. Okay. Jabana, your answer. Put R equal to 1 ohm in equation number 1. So we'll get 0.5 is EMF divided by 12 plus small r is 1. So it's 0.5 is E by 13. So your E comes out to be 0.5 into 13. So it comes out to be 6.5 volt, not 12.5. So is it clear now? Sure. Okay. So that was about terminal potential difference, internal resistance, and EMF resistance. That's it. Now, I don't want to start, the next topic is basically combination of cells, series and parallel combination of cells. I don't want to start series and parallel combination today. We have just 3 to 4 minutes left. So I'll stop here, but if you have any doubt, we can discuss it. We'll continue series and parallel combination of cells next week. If you have any doubts, we can discuss it right now. Next class is on Tuesday. Yes, if I didn't inform you, then this is on our normal timings, Tuesday and Thursday. If there is any change in timings, I will let you know. I will first take your confirmation, then I will change. Until then, it's Tuesday only. If I change timing, I'll first take your confirmation, then I will change. Okay, let's stop here. We'll continue this next week. We don't